Start recording because all the rest of that was nonsense. So this is page 21, number 6. So we have silver in our beaker, Ag plus, Mg2 plus, and strontium, Sr2 plus. We must separate them out one at a time. So silver, magnesium, and strontium. So why don't I erase some of this nonsense so we can actually see what's going on here. There we go. So we want to get out, silver is probably going to be the easiest. And I know this because silver is low solubility with most things. And in fact, if you're trying to separate out cations, usually you're going to find the cations higher up on the table are the ones you want to do first. And the ones lower down on the table are the ones you'll do later. That's just a little hint. So out of my ions, I'm probably going to do silver first. I'll do strontium second. And I will do magnesium third. So when you're separating cations, it actually makes a lot of sense to work your way down the table. Okay, because you're starting with the things at the top of the table will precipitate with almost everything down below. So silver, you'll notice silver precipitates with bromide or iodide. So silver precipitates with all those, and silver precipitates with this, and silver precipitates with that, and silver precipitates with everything down below it. Yes? And I think this is why they organized the table in this particular order. Then if we look at strontium, this one's not quite as clear-cut. We do have strontium here, then strontium's up here, and it's up here, and then it's not as soluble. And then magnesium really doesn't show up until way down here. Whoops. Because magnesium is always up in the all others and that sort of thing. So what will we do to actually solve this is we would want to add chloride. We'll go with chloride because it's easy. Sulfate and hydroxide. Whoops. So we're going to do chloride, sulfate, and hydroxide. Chloride will take out the silver, sulfate will take out the strontium, and hydroxide will take out the magnesium. So if we were to talk about how to do this, if we were to describe how to do this, we would, number one, add an excess of NaCl, not just Cl minus, but NaCl. Remember, with our negative ions, we want to pair them with sodium because sodium is unreactive and it will not precipitate ever. And now we're not wondering if silver is present. We know it is there. So we can say AgCl will precipitate. Centrifuge and decant to remove the precipitate. Now, we've gotten rid of all the silver. So if we go back to our data pages, because silver is gone, we don't have to worry about it precipitating at the same time as the strontium. Now we can do the strontium because the magnesium will not precipitate with the sulfate. That's why we're choosing sulfate next. Okay. So number 2, we want to add how much? An excess of what? Na2, SO4, and strontium sulfate, SrSO4, will precipitate. Centrifuge and decant to remove the precipitate. And if I were writing this in a question, like if I had this to do, I would be like C and D. And then later on I would be like C and D, centrifuge and decant, because I've defined it. Or maybe actually I probably wouldn't do plus because that's like a chemical thing. I'd go centrifuge and decant. There we go. And then number 3, we also need to remove our last ion, which is the magnesium. And if we go to our data pages, we chose hydroxide, although we could have chosen phosphate or carbonate or sulfite. And it doesn't matter that silver and strontium are down here because they are already all removed, okay? So we would go back here and we would say add an excess of, we wish to add hydroxide, but we cannot just add hydroxide. We will add sodium hydroxide, MgOH2, will precipitate, centrifuge, and decant to remove the precipitate. So, if you're wanting to remove negative ions, work your way down the chart, okay? That works nicely, usually. So that was number 6. Number 7, let me grab the question. We have a solution which contains either zinc or copper 1 or both. So for question number 7, we have zinc or copper +1 or both. Oh, look at this. Once again, we are trying to separate cations. So let's start at the top of our chart and see which one will precipitate first, zinc 2+ or copper 1. I think I know which one it is. Woo! So up at the top of the chart, we have copper 1. And actually, this is really good that you asked this because I wanted to point this out. I did not mention it last time when we talked about it. This is copper 1, not copper 2. So watch out for that. If you're writing a double replacement reaction and you have copper 2 chloride will not form a solid. Okay, copper 2 iodide will not form a solid, only copper 1. Okay, so watch out for copper. Okay. All right, so we could use either chloride or bromide or iodide to remove the copper 1. I would say choose chloride because it is the most common of those 3 ions. Okay. And then we wanted zinc. So we'll go down until we find something. Zinc's not here. Zinc is here. Hey, let's use sulfide then. So I'm going to use chloride and sulfide. So chloride will be used to remove the copper, and what was the other one? Sulfide will be used to remove the zinc. Alternately, you could choose hydroxide to remove the zinc, or phosphate, or carbonate, or sulfite. They would all remove the zinc because the copper one is already gone. Okay, number one, add an excess. Add an excess of, now remember we wanted to take out the copper first, okay, because if I add S2 minus first, it would precipitate both the zinc and the copper, and that would be a problem. So I'm going to add an excess of NaCl. And in this case, we're like, is there zinc? Is there copper? Are there both? So now we say if a precipitate forms, Cu plus was present. If no precipitate forms, no Cu plus was present. Present, there we go. I would, just like, I don't know how necessary it is. I would write it just because that's me, but it's probably fine not to. Do you know what I mean? Because it does, yeah. So if a precipitate forms, copper plus was present. If you have a PPT, centrifuge and decant to remove. Number two, we have sulfide to remove the zinc. So we will add an excess of Na2S. If a precipitate forms, Zn2 plus was present. If no precipitate forms, Zn2 plus was not present. If the precipitate is present, actually, you don't even need to do that at this point because it didn't ask you to separate it out. You discovered that you got there. I don't know. Let's see. What did the question ask us? 7. Design a process by which you could determine which ions are present. If you just got the precipitate and you just wanted to know if the zinc was there and it's your last ion, you don't actually have to do the centrifuge and decant. Okay, but if you choose to, there's no problem with that. You can centrifuge it and decant it. Are we good? Okay. Number 8, for sure. Number 8. There's a lot. Okay, do you want me to just do the first couple or so? Yeah, okay. And maybe actually I will do A and C because I've got chloride in both of them, and that's a little boring if I've got lead chloride and silver chloride. So I want to create a precipitate of lead 2 chloride. So I need something that contains lead ions, but I want it to be soluble because I need a solution. Who can I pair lead with that's soluble always? I can put lead with nitrate. Okay, so I got my lead with my nitrate. And that means that it is aqueous. I wouldn't want to pair lead with sulfate because that is a solid. I wouldn't want to pair it with sulfide because that's a solid. In fact, if I paired it with almost anything, it's a solid. Lead is a very insoluble type of species, okay? And I would put it together with something that contains chloride. Who would be a good ion to put with the chloride? Sodium, okay? So we wanted to have lead, we wanted to have chloride, and the ions we pair them up with should be always soluble ions. Okay, let's do calcium phosphate, Ca3PO4. So we need some calcium ions. Now that you know how to do this, it should be pretty straightforward. Who should we pair calcium up with? Nitrate. NO3, 2. And who should we pair phosphate with? Sodium, Na3PO4. And that's it. So it's pretty straightforward once you get the hang of it. Okay? Anything else? Yes? Number 4? Yeah. Okay, a solution is known to contain one of these ions. We have magnesium, calcium, strontium, or beryllium. Now, when we added Na2S, there was no precipitate. Do we care about the S or the Na? Not really. So we're just looking at S2 minus, and we're looking at SO4 2 minus, and we're looking at OH minus. And what I'm going to do actually is I'm going to grab this and I'm going to bring it over to our data pages so we can look at both at the same time. And I'm going to erase all my nonsense once again. Make it smaller because right now it's too big. Okay. All right, so we need to have sulfide giving no precipitate, and our ions are Mg 2 plus Ca 2 plus Sr 2 plus and Be 2 plus. And we want to say which of those ions gave no precipitate with sulfide. So sulfide will not precipitate with beryllium or magnesium or calcium or strontium. Oh, we've made no progress whatsoever. Yeah? So that was no help. Let's hope sulfate gets us a little bit better. We did get a precipitate with sulfate. Calcium will give us a precipitate with sulfate. Strontium will give us a precipitate with sulfate, but magnesium and beryllium will not. So, now we've eliminated a couple of possibilities. Okay? And finally, NaOH gives us no precipitate. And the only one that we're left with then is strontium. Is that good? Cool. Do you guys follow that? Excellent. All right. Anything else? We're good? How did your titration question go?
Not well.
Not well? Okay. Now, I would like you all have some piece of paper somewhere, okay? So if you need to go get a piece of paper, go get a piece of paper. Don't try and write it down on some like little scribbly thing somewhere. Okay? So you guys are going to tell your partner what is step 1 in a titration calculation. What are you finding? Always finding moles. Any stoichiometry calculation, you're always going to find moles. Moles of what? Whatever you can find moles of. There's only going to be one thing in the question where you have enough information to find the moles. Okay, there will only be one thing that gives you enough information. Let's say I gave you 15 milliliters of A, and the concentration of A is equal to 0.50 molar. And let's say I gave you, so that's the information related to substance A. Say substance B, I told you that you have 25.0 milliliters of solution B. Which of those could you find moles for? A. So you have to go through the question and find the things where it's like, oh, I have enough information to find moles. So you're going to find moles of whatever you have enough information to find moles. This is also known as your known substance. It's the one that the question is not asking you about. The question asks you about the unknown. Yes, the question says, what is the concentration of B? Okay, so maybe they say, what is the concentration of B? Or maybe they say, what is the volume of B? Or what is the mass of B? If you're asking a question about it, do you know about it? No, it's your unknown. Okay, so when you see the question words, what is B? Question words. Or you could have calculate something about B. Okay, that's another sort of question word. Okay. Question words tell you that that is your unknown. Okay, so step 1 was to find the moles of the known substance, the one they're not asking you about. What is step 2? Find moles of the unknown. So what's step number 1? Find moles. What's step number 2? Find moles. Step number 1, find moles. There's only going to be one thing you can find. Step number 2, find moles. And you'll be like, well, I already have moles of this, so it must be moles of that. Yes? So what's step number 1? Find moles. What's step number 2? Find moles. Oh my gosh. Okay, and then step 3 is going to be do what the question asks you to do. If it wants you to find the concentration of B, you're going to take the moles over the liters. If it wants you to find the volume, you'll do a conversion to find the volume. Okay? So step 1, find moles. Step 2, find moles. So what are the first 2 steps of any titration problem? Finding the moles and finding the moles. What do you need to do this step here where you convert from moles of one thing to moles of another? You must have a mole ratio, which means you need a balanced equation. Okay, so to go from here to here, you need a balanced equation. Now, while we're here, how do we find concentration? Concentration is equal to the moles over the liters. So if you're asked to find concentration, this is going to be step 3. Concentration, moles of B over liters of B. Or let's say I gave you the concentration of B, and I wanted to say what was the volume of B. What's volume measured in? Volume is measured in liters. Okay, we're going to go with liters. You can do stuff with milliliters, but for now, let's just transpose everything into liters. So you would need to cancel. What would you need to cancel here? You would need to cancel moles of B, and you would need to find liters of B. This would have to be given in the question. What the heck is a liter per mole? It's moles per liter upside down, okay? Liters per mole is moles per liter upside down. So you just take your molarity, right? Because moles per liter is just the molarity, and you flip it on its head, okay? Shall we look at our question and see how this relates to it? Okay. So now where were we? We were on... Was this us? No, that was my other block. I taught it better in the other block, so if you want to watch them, you can watch their lesson. Sometimes I do a better job the second time. Anyway, so that's why I try and record block 8, because often I sort of like, I'm like, oh, I should have done it this way. Oh, I should have done that. So anyway, you'll notice here, what's step number 1? Find moles of AgNO3. And then next step is to find our unknown moles of Cl2. So step number 1, we know that we have 11.97 milliliters and 0.100 moles of AgNO3 per liter. Okay? So we would say 0.011 0.97 liters of AgNO3. And if we want to find moles of AgNO3, why am I writing equals? I should have written multiplied by, be a time sign. Who goes on the bottom and who goes on the top? Liters go on the bottom so that they will cancel out, yes? And moles go on the top because that'll give me moles of AgNO3. Now you'll notice we were told that we have 0.100 molar AgNO3. That means we have 0.100 moles per liter. Yes? So I would always advise when you're doing a titration to rewrite capital M as moles per liter. Okay? Rewrite capital M as moles per liter. You can write Ag instead of AgNO3. That's totally fine. Okay, there's many different ways of writing this problem where you still get to the same result. Okay, so now we have 0.100 moles of AgNO3. Do we like doing all our calculations in one line or do we like splitting it up? Or do we care? One line? Okay. So now we have moles of AgNO3. We need to find moles of Cl. So we need to cancel moles of AgNO3. So that must go on the bottom and we need to have moles of Cl on the top. Now, as a chemist, you should know that because we have one Ag in one AgNO3, I can say that this 1-to-1 ratio is the same as that 1-to-1 ratio. So this is 1 to 1. Personally, if it were me, I would probably, to be honest, I would write it as Ag plus, and I would get rid of my spectator ion. And then I'd be like, okay, Ag plus and Ag plus. But you can leave the spectator ion in if you prefer. Okay, your choice. Now, at this point, this is where I would often say, just stop right here and say, okay, we have 0.00197 liters of Ag plus. Moles of Cl minus. What am I writing? Oh my God. Moles of Cl minus. Yes. 1, yes, I forgot a 1. Thank you. 0, 0, 1, 1. Okay, close enough. Good. I'm leaving that space in between every 3 digits. That's what I'm doing. All right. And so now we are asked to find, and you have to say, what is the question actually asking me for? It's asking me for concentration of chloride. And concentration of chloride, I would recommend that when you write it out, you write moles of chloride over liters of chloride, because I don't want the moles of the mixture of the silver solution and the chloride solution. Right? How much chloride is actually left once I've mixed it with the silver? When I mix my 11 milliliters of AgNO3 with my 10 milliliters of chloride, how much is left at the end of the titration? how much chloride is left at the end of the titration? Nothing. That was the whole point, was to react it all. So would there be any point in adding up my 10 milliliters and my 11 milliliters and trying to find the concentration of chloride in that 21 milliliters? No. I want to know the concentration of chloride. This was a sample of well water. It was 10 milliliters of well water. I want to know how much chloride there was in the 10 milliliters of well water. So we're going to use that 10 milliliters here. So we have 0.001197 moles of Cl minus over liters of chloride, which is 0.001000 liters of chloride, which is equal to, is that 1.197? Did I do that right? No, 10 should be here. I put one too many zeros. I'm sorry. 1000. So my answer will be 0.1197 moles per liter of chloride. Is good? Okay. Now, for those of you who want to like fine tune it a little bit, the rest of you can just tune this out because I find most people hate millimoles. And they're like, millimoles, what is that? So most of you can tune me out, but for those of you who are interested, we can actually just use 11.97 milliliters of Ag plus times 0.100 moles of Ag plus per liter. And the liters cancel, but the milli does not. So right now, what I have found is I have found millimoles of silver. Okay? And then I would still have 1 mole of chloride over 1 mole of silver. Okay, and I would still get, and I would get 1.197 millimoles of chloride because my moles of silver cancel. Okay, so I have millimoles. Millimoles. But you'll notice I'm not writing as many zeros. It's kind of nice, right? So if you like this, it can be a little bit sweet. You just have to remember to be consistent. Now what I can do is I can say my concentration of chloride is equal to my 1.197 millimoles of chloride. Now I will use my volume of chloride in milliliters, so 10 milliliters of chloride. My millis cancel out now. And I can do this because I'm using milli on the top and I'm using milli on the bottom. And I still get 0.1197. That should have been a 7 up here, but whatever. Okay. Moles per liter. Is good? All right. So if you like milli, you can use it. Don't feel obliged. If you're like millimole, confusing, no, thank you. Nope, nope, nope. It's all good. Okay? Any other questions? All right. Very good. Pardon me? Oh, number 4. Didn't we do number 4? Hang on. 3.1. Number 4. We finished number 4, didn't we? Oh, number 4 there. Oh, I get you. Gotcha. Okay, so 3.2a. There we go. Okay, yeah, we should do example number 4, and this is in 3.2a. So that's that little extra thing that you got yesterday. Okay. So that's that extra thing you got yesterday, example 4. Anyone not get that extra thing? Okay, we all got that extra thing. Excellent. Calculate the concentration of the chromate ion, CrO4 2- in a saturated solution of CaCrO4. KSP equals blah. So do you remember whether you will use the precipitation equation or the solubility equilibrium equation? Solubility equilibrium equation. Because we are told it is a saturated solution, that tells us it's the SEE. And we have a KSP that also tells us it is the SEE, the C. And we're not going to do the question today. If you want to try it on your own, you can try it on your own and take a look. Okay? But we'll actually officially learn it later on. Or would you like to learn it today? Yeah? Okay. So here we have CaCrO4. It is saturated, so we have an equilibrium. All right. And so we would write the C, CaCrO4 solid in equilibrium with Ca 2 plus CrO4 2-. Now, we know we want to find the concentration of the chromate ion. That is our unknown. So why don't we call that X? Yes? Okay, so concentration of the chromate ion is X molar. If concentration of chromate is X, what is the concentration of calcium? Also X, because they are 1-to-1. And now, what could we write that would help us find X? We could write the KSP expression. So we would write KSP is equal to concentration of calcium times the concentration of chromate. And we are told that KSP is 7.08 times 10⁻⁴. And we know that each of those concentrations are X, so we have X squared. So X is now equal to 7.08 e⁻⁴ square root 0.0267. And we have 3 sig figs here, and we have 3 sig figs here. And we should write, because we were finding the concentration of chromate, molar CrO4 2-. Pretty easy, yeah? Okay. Okay. Now, I'm going to jump to my other copy of this thing whenever you guys are finished. Okay. So back to our solubility product constant. Remember we said yesterday, if you have a smaller KSP, what can you say about the solubility? Lower solubility, because you will have lower ion concentrations. If you have a smaller KSP, you have lower ion concentrations. And some of our KSP values can be as small as 10 to the negative 30, or 10 to the negative 50, or 10 to the negative 70, or crazy things like that. Some of them are just 10 to the negative 12, but some of them are crazy insoluble. Now, this fact that your solubility is lower with a smaller KSP, we can use this to rank salts that have the same ion ratio, but they have to have the same ion ratio. So let's take a look at these salts here. How many silvers do we have for every carbonate? We have a 2 silver to 1 carbonate ratio, yes? 2 to 1. What is the ratio of barium to fluoride? 1 to 2. And for the purpose of this 2 to 1 is the same as 1 to 2, okay, in terms of ion ratio. The KSP doesn't care whether it's a positive ion or a negative ion. And for lead hydroxide, we also have a 1 to 2 ratio. So if I look at this and if I say I have the same ion ratio for each of these, maybe I have this in a written response and they're like, please rank these from the most to the least soluble. Who is the most soluble? Tell your partner. And who is the least soluble? Did we get that barium fluoride was the most soluble? This is our largest number. And who is our smallest? Lead hydroxide. Now, let's see how much room I left here. Yeah, okay, that's good. So there's our ranking. Now, I actually wanted to show you why this works for like the 2 to 1, okay? If we take Ag2CO3 and we dissociate it according to the solubility equilibrium equation, we get 2Ag plus, and we get CO3 2 minus. If we don't know the concentration, we could call the concentration of carbonate X, yes? What would that make the concentration of silver? 2X. Okay, and the concentration of Ag2CO3, which I'm putting in brackets because it is a solid, what would we call that? X, because it's a 1. It's got a coefficient of 1. Then if we were to write our KSP expression, silver squared, yes, times carbonate silver is 2x, and I square it, carbonate is X. And so we end up getting 4, because 2 squared is 4, and then we square the X, so we get X squared times X is X cubed. Yes? Does that make sense? Okay. So that's what happens if our cation is the one that has the 2. All right, let's take a look at BaF2 to prove to ourselves that we'll end up with the same equation if it is the anion that has the 2. So we could write down here, we have BaF2, our solubility equilibrium equation for BaF2 equilibrium arrow, Ba2 plus 2F minus and if I say, let's let barium be X, that means fluoride is going to be 2X. And that means the concentration of barium fluoride is X molar. If we then write our KSP expression, KSP, we have barium times fluoride squared so what we end up with then is we end up with barium is X, fluoride is 2X, we have to square the whole thing. So we end up with X times 4X squared, which is going to give us 4X cubed. And guess what? That's identical to the other one because KSP doesn't care whether you have a positive ion or the negative ion as the X and the other one is the 2X. Yes? Why did I have a 2X? So that 2, good question, comes from the coefficient. So if you have barium fluoride and if you have one of them, it dissociates into 1 barium and 2 fluorides.
Didn't you put that 2 and put it square?
Oh, yes. Okay, so I have done that. So this 2 becomes this 2. But if I were to ask you, what is the concentration of fluoride? The concentration of fluoride is 2X. Not the concentration of 2 fluorides, but the concentration of fluoride is twice the amount. So let's just use some real numbers here. If the concentration of barium was 0.1, the concentration of fluoride would be 0.2. And then you would plug that into your equation and you would say I have 0.1 times 0.2 squared. Does that make sense? Yeah, good question, because it is a little boggling that way. All right, so that's an interesting point. And this will actually come in handy in multiple choice questions where they're like, please find this concentration of a saturated solution of BaF2. You can be like, if it's a multiple choice question, you can say my concentration is X. And I know that for a 2-to-1 compound, KSP is equal to 4X cubed, and you can just solve for X. It makes your life really fast. We're not there yet, but that's where this can take you if you know these patterns. Now, using this method only works. The method of comparing KSP values only works for the same ion ratios. So you could compare Al2CO3, Cr2SO3, and Mn3PO for 2, because you always have 2 to 3, 2 to 3, or 3 to 2. Those are all the same. You could compare those. You could compare AG, which has no subscript, CL, which has no subscript. That is 1 to 1. CA has no subscript. CO3, there's no brackets, so there's no subscript here. So that is also 1 to 1. PBS, no subscript, 1 to 1. So you could say, oh, the KSP of calcium carbonate is bigger than these other two, so it is more soluble. But you cannot do that. You cannot just say bigger KSP, more soluble, if you're comparing a 1 to 1 to a 1 to 2 to a 3 to 2. And the reason for that is that for this one, KSP is going to be equal to x squared. And for this one, KSP is going to be equal to 4x cubed. And heaven forfend, we have this sucker over here. I don't even know what that would be. It makes me sad to think about. It would be 3x cubed times 2x squared, which would be 27x cubed, which would be times 4x squared, which would be 108x to the 5th. Okay, so don't even bother with something this big, like to try and like learn its pattern, because it's just easier to figure it out. And we'll look at that much more in depth later. When we start doing the actual KSP math, it'll become much more evident. But for now, all you need to know is if your ratio is the same, you can compare solubilities by comparing KSPs. But if you have different ratios, you cannot compare that same way. Is good? All right. Writing KSP expressions. You always get a mark for writing the dissociation, or actually this should be the solubility equilibrium equation. I'm just going to call it solubility equilibrium equation. Okay, that's worth 1 mark. Or 0.5 actually, 0.5 marks. Write the KSP expression. Could you write the KSP expression for this one? Is good? Okay. Could you write the KSP expression for MgOH2? And remember, before you do that, you need to write the C. Okay, so write the C first. We all good with that? Okay. Good. What else we got on here? Oh, there's some exercises. Excellent. Why don't you work on those exercises a little bit? Yeah? And then your homework is to study for your quiz. So yes, do some exercises here and study for your quiz. Quiz is 3.1. Okay, just 3.1.
Yeah, we don't need that.